The watchman crosses the bridge at 10:30. His boots strike iron deck plates in slow rhythm. Gas lamps glow pale along the railings, their light pooling on wet steel and fading into the dark span ahead. Below, the river moves without sound. Above, the truss rises into shadow, diagonal braces, vertical posts, top cords vanishing overhead into cold October air. He walks the centerline, always the centerline. Deck is wide enough for 2 wagons, but at night he keeps to the middle where the structure feels most solid beneath him. The bridge was built 3 years ago, steel from Pittsburgh, bolted connections throughout. It carries freight during the day, coal wagons, timber loads, iron castings bound for the mills downstream. By night it carries only him. Halfway across he stops. There is a sound, not sudden, not loud. A low creak rising from somewhere deep in the framework. He stands still, listening. The sound continues, steady, rhythmic, like a rope pulled taut in very slow motion. He looks up into the truss. The diagonals angle away into darkness. The verticals rise clean and straight. Nothing moves, but the sound persists. He takes another step. The deck plate rings under his boot. The creak pauses, then resumes, deeper now, as if the structure is settling under his weight. But he's walked this bridge 100 nights. It never sounded like this before. He moves forward. The sound shifts. Not louder, not faster, just tighter, as if the metal around him is drawing inward. He reaches the far abutment and steps off onto gravel. The sound fades behind him. He turns back. The bridge sits motionless in the lamplight, solid, silent, exactly as it should be, but it wasn't silent a moment ago. He writes nothing in his logbook that night. There's nothing to report. No damage, no movement, just sound and the feeling, faint but certain, that the bridge had been holding something back. The sound returns the next night, same time, same location. The watchman hears it again at the center span, that low metallic groan rising from the truss overhead. He stops, listens, moves on. By the time he reaches the far side, the noise has faded. He checks the bridge at dawn. The deck is dry. The joints are clean. The bolts sit flush in their holes. Everything is normal. The third night, he brings a lantern. He walks slowly, holding the light high, letting it sweep across the lower cords and connection plates. The shadows shift. The ironwork gleams. The sound begins again, not from one point, but distributed as if the entire structure is involved. He kneels and places his palm flat against a deck beam. He feels it. A faint vibration, rhythmic, steady, like a pulse. He stands. The vibration fades. The sound continues. By the end of the week, the pattern is clear. The bridge tightens after sunset. It begins around 10 o'clock, when the air has cooled and the last of the day's traffic has cleared. It continues for hours, sometimes until midnight, sometimes longer. By morning it stops. The structure returns to silence. No cracks appear. No bolts loosen. The bridge functions perfectly under load during the day, but at night something is happening. The watchman reports it. The bridge company sends an inspector. He walks the span at noon, examines the connections, measures the expansion joints. Everything is within tolerance. The joints are open. The bolts are tight. The inspector finds no evidence of distress. He recommends continued monitoring and returns to the city. That night, the bridge tightens again. The watchman hears it from the approach. He doesn't need to be on the structure anymore. The sound carries. A low, sustained groan, like weight settling onto a beam that's already loaded. He writes it in the log this time. Audible strain in main span. No visible cause. Occurs nightly after 10 p.m. He doesn't write what he thinks, that the bridge is pulling itself together in the dark, that it's doing something steel isn't supposed to do, that it sounds, more than anything else, like a structure preparing to hold a load that hasn't arrived yet. By November, the sounds are louder, not dramatically, not suddenly, but measurably, consistently louder each week. The watchman no longer needs to stop and listen. He hears the strain from the abutment before he steps onto the deck. A deeper groan now, more sustained, with a faint metallic ring underneath. The kind of sound a bolt makes when it's being tightened past snug. He walks the span with his lantern every night. He's learned where to listen. The loudest sounds come from the center, where the truss is deepest and the span is longest. But the noise isn't isolated there. It travels. He hears it near the expansion joints at each end, where the bridge is supposed to slide freely on its bearings. He hears it at the connection plates, where diagonal braces meet the verticals. He hears it in the deck itself, a faint hum that rises through the iron when he kneels and presses his ear to the metal. One night in mid-November, he finds the first. It's on a bolt head near the lower chord, about 20 feet from the center pier. A thin, bright line scraped into the rust, just a sliver of clean metal, as if something has shifted and scribed the surface. He marks the location with chalk. The next morning he brings the inspector back. The inspector examines the bolt. The mark is fresh. The surrounding rust is undisturbed, which means the movement is recent, within days, maybe hours. But the bolt itself is tight. The inspector tries to turn it with a wrench. It doesn't move. He checks the adjacent bolts. They're tight too. He checks the connection plate. No cracks, no deformation. Witness mark, the inspector says. Something moved here, but the bolt didn't loosen. No, it tightened. The inspector doesn't explain further. He measures the gap at the nearest expansion joint. It should be 3/8 of an inch. It measures 5/16. Narrow, but not outside tolerance for late autumn. He checks the other end of the bridge. That joint measures the same. Both ends are slightly closed, not enough to be dangerous, just enough to be noticed. He makes notes. He recommends another inspection in 2 weeks. That night the bridge tightens again. The watchman hears it. He walks the span and finds 2 more witness marks, one on a vertical post, one on a diagonal brace, both fresh, both on bolts that are seated firmly in place. He doesn't report them immediately. He waits. He wants to see if they multiply. They do. By December, there are dozens of marks. Fine scratches around bolt heads, scribed into paint and rust, as if the metal is creeping incrementally under load. The expansion joints measure tighter. The sounds at night are no longer intermittent. They're continuous. A low, sustained groan that begins at dusk and holds until just before dawn, when the air warms and the tension finally breaks. The bridge is still safe. Traffic crosses daily without incident. But at night, the structure is doing something it wasn't designed to do. It's loading itself. Steel truss bridge is designed to move, not visibly, not dramatically, but predictably in small increments as temperature changes throughout the day. Steel expands when heated, contracts when cooled. A bridge 300 feet long can grow or shrink by more than an inch between summer and winter. Engineers account for this. They install expansion joints, sliding bearings at each end that allow the structure to lengthen and shorten without building up internal stress. During the day, the bridge heats. The steel expands. The joints slide outward. At night, the bridge cools. The steel contracts. The joints slide inward. The cycle repeats daily, harmlessly, as long as the joints remain free to move. The forces involved are substantial. A long steel member contracting even a fraction of an inch can generate thousands of pounds of tension if it's prevented from moving. But bridges are not prevented. They're designed to accommodate thermal movement through the joints, which act as relief points, places where the structure can breathe without accumulating strain. That's the theory. In practice, expansion joints can fail quietly. Rust builds up on the sliding surfaces. Dirt and debris pack into the gaps. Water freezes in the joint and locks it in place. Over time, a joint that was designed to slide freely can become stiff, or worse, completely immobile. When that happens, the structure can no longer move as intended. Instead of sliding at the bearings, it begins to deform internally. Members go into tension or compression, bolts experience shear, connection plates flex. The structure tries to accommodate the thermal movement by bending, twisting, or compressing itself. Usually this results in cracking. A locked joint puts stress where stress wasn't expected. Welds fail. Rivets pop. Paint flakes off at high-strain areas. Inspectors find the damage and repair the joint. The bridge returns to normal, but sometimes the structure is strong enough to absorb the stress without visible failure. It simply holds it. During the day, the bridge expands under heat and traffic load. Tension builds in the members, but it's balanced by the weight of passing wagons, by the compression in the top chords, by the geometry of the truss itself. At night, the traffic stops. The bridge cools. The steel contracts. The expansion joints, if they're locked, don't allow the structure to shorten. Instead, the contraction generates tension throughout the truss, pulling the members tighter, drawing the joints closed, accumulating strain that has nowhere to go. If the joints unlock at dawn, the strain releases. The bridge returns to equilibrium. No damage occurs. Just a nightly cycle of loading and unloading, invisible to anyone not listening. But if the joints don't unlock, if the friction is high enough, if the contamination is deep enough, The strain doesn't fully release. It accumulates. Night after night, the structure pulls itself tighter. The sounds grow louder. The witness marks multiply. The bridge begins to live in a state of perpetual tension, held together not by its design, but by its own inability to let go. That's what should not be happening. But on this bridge, in the winter of 1888, it is. The expansion joints are packed with rust. The discovery comes in January, when the bridge company finally sends a maintenance crew to inspect the bearings. The watchman leads them to the south abutment, where the bridge rests on a cast iron sliding plate. The plate should move freely on a bed of graphite-coated steel. It doesn't. The crew pries up the deck plates and exposes the bearing surface. The graphite is gone, worn away or washed out. The iron has corroded. The sliding surfaces are locked together by a layer of rust and frozen grime. They move to the north abutment. Same condition. Both bearings are seized. The crew cleans them. They scrape away the rust, apply fresh graphite, test the movement. The bridge slides, just barely. The friction is still high, higher than it should be. But the joints are no longer fully locked. The crew finishes the work and departs. That night the bridge tightens again. The sound is quieter, not gone, just reduced. The watchman walks the span and listens. The groan is still there, but it's smoother now, less jagged. He checks the witness marks. No new ones appear. The old marks remain, but they don't grow. For a week, the bridge is quieter. The joints slide. The strain seems to release. But by mid-January, the sounds return, louder than before. The watchman reports it. The crew returns. They inspect the bearings again. The graphite is still in place. The surfaces are clean, but the joints aren't moving. They're stiff, so stiff that even with pry bars, the crew struggles to shift the bridge on its bearings. They eventually succeed, but the effort required is significant. Friction's too high, one of them says, even with fresh graphite. Why? Don't know. Maybe the load's too heavy. Maybe the bearing angle's wrong. Maybe the joint's just been locked too long and now it doesn't want to move. They try oiling the surfaces. It helps, but only slightly. The bridge still resists. They leave it as free as they can make it and return to the yard. That night the bridge tightens again. The watchman hears it. The sound is different now, sharper, more localized. He walks to the center span and kneels. He presses his hand to a lower chord. The vibration is stronger. He moves to a vertical post and does the same. The metal hums under his palm. He looks up into the truss. The diagonals angle away into shadow. The connection plates are invisible in the dark. But he can feel it, transmitted through the structure, through the bolts and beams and braces, a slow, sustained pull, as if every member is trying to shorten at once. He stands. He walks to the nearest expansion joint and examines it by lantern light. The gap is narrow, narrower than it was this morning. He measures it with a folding rule. 3/16 of an inch. It should be 3/8. The joint has closed. He crosses to the other end. Same measurement. Both joints have closed. The bridge is shorter than it should be. By morning, the joints are open again. The gap measures 3/8 on both ends. The bridge has lengthened. The cycle has completed, but the cycle is not neutral. Each night the bridge contracts. Each morning it expands. And somewhere in between, the structure is holding tension that doesn't fully release. The sounds prove it. The witness marks prove it. The friction in the joints proves it. The bridge is not failing. It's not cracking. It's not visibly deforming. But it's doing work. Every night, the steel members pull against each other, generating strain, storing elastic energy in the truss. Every morning, that energy is supposed to release. But it doesn't, not completely. Some of it remains, locked into the structure by friction, by contamination, by the geometry of the connections themselves. The bridge is ratcheting. Slowly, incrementally, it's tightening itself. The bridge company shuts down the structure in February, not permanently, just long enough to conduct a full structural survey. Engineers arrive from Pittsburgh with instruments, strain gauges, calipers, theodolites, thermometers. They measure everything: joint gaps, bolt torques, member lengths, deck elevations, bearing positions. They map the entire bridge in 3 dimensions and compare the measurements to the original design drawings. The structure is out of tolerance, not by much. 1/16 of an inch here, an eighth there. But cumulatively across 300 feet of truss, the deviations add up. The bridge is shorter than it should be, compressed, as if under permanent load. The expansion joints are open, but barely. The bolts are tight, but some are tighter than others. The witness marks are everywhere, hundreds of them, scribed into metal at nearly every connection. The engineers take temperature readings over a full day and night cycle. They record the air temperature, the deck temperature, the truss member temperatures. At dawn, the steel is cold, near freezing. By noon, it's warmed by 15 degrees. By dusk, it's cooled again. By midnight, it's colder than it was at dawn. They measure the expansion joints throughout the cycle. During the day, the gaps widen as the bridge heats and expands. At night, the gaps narrow as the bridge cools and contracts. But the movement is not smooth. The joints stick. They bind. They resist motion until the thermal force is high enough to overcome the friction, and then they slip suddenly, releasing the built-up strain all at once. The engineers record the sounds. At night, they hear what the watchman has been hearing for months: the low groan, the metallic hum, the faint pinging of bolts under tension. They place strain gauges on the lower chords and measure the force. The members are in tension, significant tension, far higher than expected for an unloaded bridge at rest. They measure again at dawn. The tension drops, not to zero but to a lower baseline. The bridge has released some of the strain, but not all of it. Residual stress remains. The pattern becomes clear. During the day, the bridge carries traffic. The load compresses the top chords and tensions the lower chords as designed. The structure is in equilibrium. At night, the traffic stops. The bridge cools. The steel contracts. The expansion joints, stiff from friction and contamination, resist the contraction. Instead of sliding freely, they bind. The structure can't shorten at the bearing, so it shortens internally. The members pull tighter. Tension builds in the lower chords. Compression increases in the top chords. The entire truss draws inward, but the structure is strong. It doesn't crack. It doesn't yield. It simply holds the tension overnight. At dawn, the bridge warms. The steel expands. The joints, which have been holding the structure in compression, suddenly release. The expansion force is high enough to overcome the friction. The bearings slip. The bridge lengthens. The tension drops, but the cycle is imperfect. The joints don't release completely. They stick again almost immediately. A small amount of tension remains locked in the structure. The next night, the bridge contracts again and adds more tension on top of what's already there. Over weeks, over months, the residual stress accumulates. The bridge is ratcheting itself tighter, night after night, cycle after cycle, because the joints can't move freely enough to fully relieve the strain. The bridge company shuts down the structure in February, not permanently, just long enough to conduct a full structural survey. Engineers arrive from Pittsburgh with instruments, strain gauges, calipers, theodolites, thermometers. They measure everything: joint gaps, bolt torques, member lengths, deck elevations, bearing positions. They map the entire bridge in 3 dimensions and compare the measurements to the original design drawings. The structure is out of tolerance, not by much. A 1/16 of an inch here, an 1/8 there. But cumulatively across 300 feet of truss, the deviations add up. The bridge is shorter than it should be, compressed, as if under permanent load. The expansion joints are open, but barely. The bolts are tight, but some are tighter than others. The witness marks are everywhere, hundreds of them, scribed into metal at nearly every connection. The engineers take temperature readings over a full day and night cycle. They record the air temperature, the deck temperature, the truss member temperatures. At dawn, the steel is cold, near freezing. By noon, it's warmed by 15 degrees. By dusk, it's cooled again. By midnight, it's colder than it was at dawn. They measure the expansion joints throughout the cycle. During the day, the gaps widen as the bridge heats and expands. At night, the gaps narrow as the bridge cools and contracts. But the movement is not smooth. The joints stick. They bind. They resist motion until the thermal force is high enough to overcome the friction, and then they slip suddenly, releasing the built-up strain all at once. The engineers record the sounds. At night, they hear what the watchman has been hearing for months: the low groan, the metallic hum, the faint pinging of bolts under tension. They place strain gauges on the lower chords and measure the force. The members are in tension, significant tension, far higher than expected for an unloaded bridge at rest. They measure again at dawn. The tension drops, not to zero but to a lower baseline. The bridge has released some of the strain, but not all of it. Residual stress remains. The pattern becomes clear. During the day, the bridge carries traffic. The load compresses the top chords and tensions the lower chords as designed. The structure is in equilibrium. At night, the traffic stops. The bridge cools. The steel contracts. The expansion joints, stiff from friction and contamination, resist the contraction. Instead of sliding freely, they bind. The structure can't shorten at the bearing, so it shortens internally. The members pull tighter. Tension builds in the lower chords. Compression increases in the top chords. The entire truss draws inward, but the structure is strong. It doesn't crack. It doesn't yield. It simply holds the tension overnight. At dawn, the bridge warms. The steel expands. The joints, which have been holding the structure in compression, suddenly release. The expansion force is high enough to overcome the friction. The bearings slip. The bridge lengthens. The tension drops, but the cycle is imperfect. The joints don't release completely. They stick again almost immediately. A small amount of tension remains locked in the structure. The next night, the bridge contracts again and adds more tension on top of what's already there. Over weeks, over months, the residual stress accumulates. The bridge is ratcheting itself tighter, night after night, cycle after cycle, because the joints can't move freely enough to fully relieve the strain. The cause is friction. Not failure, not defect, just friction, ordinary, predictable, and in this case, cumulative. Steel contracts when it cools. A bridge 300 feet long will shrink by roughly an inch between noon and midnight on a cold autumn night. If the expansion joints slide freely, that contraction is harmless. The structure shortens at the bearings, and no internal stress develops. But if the joints are stiff, if rust has built up on the sliding surfaces, if dirt has packed into the gaps, if the graphite lubricant has worn away, the structure can't slide as easily. The contraction force must overcome the friction before the joint will move. Until that happens, the steel tries to shorten by compressing or tensioning internally instead. On this bridge, the joints were stiff enough that the thermal contraction force wasn't always sufficient to move them. Instead of sliding smoothly throughout the cooling cycle, the bearings would stick. The structure would contract against the resistance, building up tension in the lower chords and compression in the top chords. Eventually, the force would overcome the friction, and the joint would slip, but only partway. It would stick again, and the cycle would repeat. Each time the joint stuck, the structure held a little more tension. Each time it slipped, it released only part of that tension. Over hours, the strain accumulated. Over nights, it grew. By morning, when the bridge warmed and expanded, the joints would slip outward, but again, not completely. A small residual tension remained locked in the truss. Next night, the process repeated. The bridge contracted. The joints stuck. More tension accumulated on top of what was already there. The ratcheting effect was subtle, just a few pounds per cycle, but it was persistent. Over weeks, the cumulative strain became significant. The sounds grew louder because the members were under higher tension. The witness marks appeared because the bolts were creeping incrementally under load. The joints closed tighter because the structure was compressing itself from within. The bridge wasn't failing. It was loading itself. The engineers identified three contributing factors beyond the friction in the expansion joints. First, residual stress from the original construction. The truss members had been assembled under load, and small amounts of internal stress had been locked into the connections when the bolts were tightened. That stress never fully relaxed. Second, the bolted connections themselves. Like riveted joints, which deform slightly and distribute stress across the fastener, bolted joints rely entirely on friction between the plates. If the clamping force increases, due to thermal contraction or accumulated strain, the joint becomes stiffer, increasing the overall resistance to movement. Third, the geometry of the truss. The diagonals and verticals were arranged in a configuration that distributed the contraction force unevenly across the span. Some members pulled harder than others. The center of the bridge experienced the highest tension, which is why the sounds were loudest there. The solution was straightforward. The engineers disassembled the expansion joints completely, machined the bearing surfaces flat, installed new graphite beds, and added spring-loaded guides to keep the joints aligned during movement. They also loosened and retightened every bolt in the structure to a uniform torque, relieving the residual stress from construction. Finally, they installed measurement marks at the joints so that any future stiffness could be detected before it accumulated. The bridge reopened in March. The sounds did not return, The joints moved freely. The nightly contraction and daily expansion proceeded as designed, silent, predictable, harmless. The structure had not been weak. It had been too strong. Strong enough to hold tension it was never meant to carry. Strong enough to pull itself tighter, night after night, without cracking or yielding. Strong enough to survive its own accumulated strain long enough for someone to notice and understand. The watchman continued his rounds. He crossed the bridge every night for another 18 years. He never heard it tighten again. But he remembered the sound, the low groan in the dark, the hum of steel under strain, the feeling, faint but certain, that the structure was doing something no one had predicted. The bridge stood for 63 years before it was replaced. By then, the story had faded. The witness marks had been painted over. The logbook entries were stored in a warehouse and eventually lost. But the lesson remained, recorded in engineering journals and passed quietly through the profession, that some structures are strong enough to fail in ways their builders never imagined. Not by breaking, but by holding on.